Okay, the last concept today is called Chebyshev's theorem. Yes, try to say it. Chebyshev. It just makes you smile, right? Chebyshev. Okay. Chebyshev's theorem is the proportion of any distribution. So I'm going to underline that. Any distribution. Any distribution. Empirical rule technically only applies to what? Normal distribution, okay? But Chebyshev's applies to any distribution. So if you have a distribution that's not normal, you can use this, all right? So it says the proportion. Proportion is another word for probability, which is what the Z table gives us, or the empirical rule gives us, 0.68, 0.95, 0.99, right? The proportion of any distribution that lies within K standard deviations of the mean is at least. Now, what's the word at least mean? That number or more, greater, okay? So it's telling me at least that proportion, but it could be more, okay? Is 1 minus 1 over K squared. So if I say find how many would be within 2 standard deviations, I would plug 2 in here. 2 squared is 4, 1 minus 1/4 is 3/4, so 75%. Done. Do you see how easy that was? But the cool thing about this is I can say how many is within 2.5 standard deviations, or 1.5. You'd plug in 1.5 squared and find it, okay? So K is any positive number greater than 1. So why doesn't it have to be greater than 1? Why does it have to be greater than 1? Let's look. What if K was 1? What would I plug in? 1. What's 1 squared? And what's 1 minus 1? So does that make sense? 0% falls within the mean and 1 standard deviation. That doesn't make sense, does it? So you have to have bigger than 1, and that's why. Okay? Because otherwise you get 0, which is not helpful. Okay. This theorem applies to all distributions of data. Let's see, I've said that how many times now in one paragraph? Any distribution, all distributions. Think that's an important thing to remember? Yes. All right, let's look. So the results of the physical fitness strength test given to some third graders are given below. Their test results are listed in rank order and are shown in the histogram. Notice it's in order from least to greatest, but instead of going down the column, it goes across the row. Do you see that? Okay. If you look at this histogram, it looks really weird, doesn't it? I mean, how would you classify this? Trimodal? Maybe? Which is weird, because there's 3 modes. Do you know what this graph tells me? Seriously. Anybody? Is this a good distribution to try to classify? No. So when that happens, I start looking at the classes down here. The mid mark of this one is 0. The mid mark of this one up here is 5, then 10. So that shows me the classes are not good. So this is a moment where you, if you made this histogram, would go, my bins are not good. I need to try to make less, maybe. Less bins to see if that changes the distribution. You know what I mean? So a moment when you have this distribution does not look normal or skewed or even bimodal, does it? It's bad. This is probably a bad graph. What do you say? Yeah. So if you make a bad graph or you don't want to use the graph, you can use the raw data itself, okay? And you can determine if it's a normal distribution or skewed somehow or not normal, okay? So how do we do that? You need your calculator. Okay, I'm going to need y'all's help to put this in my calculator, okay? So you go to Stat, then Edit, and we're going to put this data in L1. But notice my L1 has data, so how do I get rid of it? up, and then clear, not delete, clear, and then I hit enter. If you hit delete, it's going to delete that list, which makes your life more challenging, because then you got to tell it L2 or L3 or whatever, okay? All right, so will y'all call out the data values for me? 1, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, 6, 6, 6, and time out. Are we on the 17th value, everybody? We put 16 in, thank you. Okay, what's the 17th value? 8, 9, 9, 9, 9, 9, 9, oops, not 4, 10, 10, 11, 12, hold on, I pressed 2 and it didn't work. Okay, I have 3 12s. 13, 14, 14, 14, 15, 15, 15, 15, 16, 16, 16, 17, 17, 17, 17. Is that it? 44 data values, y'all agree? Now, could you calculate by hand the mean and the standard deviation? Absolutely, but do you want to? No. So we're going to go to stat. There's more data?
Yeah.
Oh, I thought we were done.
No, I just wanted to take a little break.
Really, right now? Really? I can't remember, I'm sorry.
So we have 18. We have 4 18s.
4 18s. 1, 2, 3, 4. Okay?
And now we have 4 19s.
4 19s. 1, 2, 3, 4.
We have 3 20s.
3 20s. 1, 2, 3,
We have 3 21.
3 21. 1, 2, 3.
3 22.
3 22. Okay?
1 23.
1 23.
And 2 24.
And 2 24. It makes me feel like it's final.
Yes.
That's it.
Yes.
For sure. Okay. All right. I know it's a lot of data, but, you know, to get a good distribution and a good idea for the population, it's good to have a lot of data. You know what I mean? And this data looks pretty close together. I mean, it went from 1 to 24, but we had a lot of values that were the same, right? So now we're going to go to stat, arrow over to calc, and do one variable statistics because we only have one variable. The list is in L1. We're going to keep hitting enter and calculate. And notice we get X bar is 13. So that's my mean. And notice we get S of X or sigma of X. So you have to ask yourself, is this a sample or is this a population? Some third graders. So it's a sample. So which one do I use? S of X or sigma of X? S of X. So we're going to write that down. 6.61. So I have a mean of 13 and a standard deviation of 6.61. I made y'all calculate standard deviation the other day. So we should be able to understand what it is and what it means, right? Everybody got those numbers? Okay, great. So it says determine the mean and the standard deviation. So let's write that down. X bar was what? 13, and S was about 6.6, wasn't it 1? Okay, so it says, is this distribution approximately normal? Well, if I look at my histogram, my answer would be no way, no. But maybe that's a bad histogram, right? We were talking about it as I pulled up my calculator. You know, maybe we should change the bins. Maybe we should try 0 to 5, 5 to 10, 10 to 15. Or maybe we should try 0 to 3, 3 to 6, 6 to 9. You see what I'm saying? You can determine your class sizes and your bins so you can change the histogram. So how can we figure out absolutely if this is approximately normal? Or if it's Chebyshev's theorem, which means any other distribution. Any ideas? Mean, median, and mode to see if they're close. That's a good idea. You could do that, then left skewed, right skewed, figure it out from that. Yes, I'm going to show you though using the empirical rule or Chebyshev's. Okay? So, the way you do that is you actually take and calculate x bar plus or minus s, and you figure that out. Then we're going to take and calculate x bar plus or minus 2s, which just means 2 standard deviations above or below, or x bar plus or minus 3s. Alright, so x bar plus or minus s. So I like to do subtraction first because it's going to be smaller. So x bar 13 minus 6.61 to 13 plus 6.61, which gives me 6.39. Is that right? Okay, and then 2, 19.61. Y'all agree? Perfect. Leave some space. I did that on purpose because we're going to come back and figure something out, okay? So leave some space. Now I'm going to do plus or minus 2s, which is 2 standard deviations above or below. So you realize if I was drawing a curve, I would put x bar in the middle 13, and then 1 standard deviation below would be 6.39. 1 standard deviation above would be 19.61. Okay? Does everybody understand that? So 2 below, once I have this number, I can just do what to it? There's a reason why I just said that to you all. If this is the mean and it's in the middle, what did I just do? I subtracted 1 standard deviation and I got 6.61, right? I added 1 standard deviation and I got 19. What? Not 61. 39, thank you. You were going to totally tell me I wrote the wrong thing, weren't you? Okay, good. Y'all got to have my back. 19.61. So if I want to find 2 standard deviations below, yes, I could do 2 times s and subtract from 13. Or I could just do what? Subtract it again, yeah. So if I subtract it and I add it one more time, 6.39 minus 6.61 is negative what? Negative 0.22. So what? I'm going to add 6.61 to 19.61, and I get perfectly? No. You get what? No. 19.61 plus 6.61. 26 point what? 22. You went from here and added it and got 13 back to the middle. Yeah. That's okay. I'm like, there's no way it's 13. Something happened. Okay, now, so with these new numbers, what can I do? Add it to this one, subtract it from that one, and we get negative what for this one? Negative 6.83 to what? Add 6.61 to this. 32.82? Oh, I'm sorry, 83. Like that? Okay, great. So why did we just do that? Well, we know that within one standard deviation, if it's normal, how much of the data is between that? If it's normal, how much is within one standard deviation? 68%. At least. It can be more, but empirical rule says at least 68% of the data. Within two standard deviations is 95, and within three standard deviations is 99. So guess what I'm getting ready to do using these numbers? Things. You're getting ready to do things. I'm going to see how many numbers fall between this and this. So can I count how many numbers are between 6.39 and 19.61? 6.39 does not count 6, does it? So it's going to start here at 8, and it's going to go up to 19. It's not going to include 20, is it? So I'm going to go to there. How many data values are between that? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's 16. This will be 16, 32, 33, 34, 35, 36. So 36 out of how many? 64. Find that percentage for me, please. 0.5625, which would be about 56.25%, right? Okay. So how many are between negative 0.22 and 26.22? Well, that would be every number, right? Because we didn't have any negatives. Up to 26, which is everything. 64 over 64, which is 1. So that is 100%. 100% of the data is within 2 standard deviations. Isn't that interesting? So is this normally distributed? Well, I wrote this word after I was writing them for you. I went back and wrote this. At least 68%. That means 68 or more. Is 56.25 at least 68? No. So is this normally distributed? No. So remember when I said 2 standard deviations for Chebyshev's? Look, this is the empirical rule, isn't it? Yes, this is the empirical rule. Chebyshev's rule says I can plug in any k as long as it's bigger than 1, right? Didn't I just calculate 2 and 3? Yeah. And it says it'll be 1 minus 1 over k squared. So if I do 2 standard deviations, I'm not going to do 1, I'll do 2. How much of the data should be within 2 standard deviations? That's 1 over, excuse me, try again, Shannon. Sorry, everybody. 1 minus 1 over 2 squared, because I'm plugging in 2 standard deviations. So that's going to be 1 minus 1/4, which is 3/4, which is what as a percentage? 75%. Is at least 75% of the data within 2 standard deviations? Yes, I got 100%. So see, Chebyshev's theorem works. Always. The empirical rule doesn't always work. So does everybody see how to do this?
Yeah.
Everybody? Okay, great. So, the scores achieved by students in America make the news often, and all kinds of conclusions are drawn based on these scores. The ACT assessment is designed to assess high school students' general educational development and their ability to complete college-level work. One of the categories tested is science reasoning. The mean ACT score for all high school graduates in 2008 in science reasoning was 20.8 with a standard deviation of 4.6. According to Chebyshev's theorem, at least 89% of high school graduates' ACT scores in science reasoning will be between what values? At least 89%. It says according to Chebyshev's theorem. See, you need to be thinking what? What is Chebyshev's theorem? Good. 1 minus 1 over k squared. Do I know the standard deviations that I use to get 89%? Is it 2? I don't know. Isn't it any number bigger than 1? So do you want to try 2 and see if that'll give me 0.89? Because then that would be my answer, wouldn't it? You want to try that? Or you could solve it like algebra. You can set this equal to 0.89. Then you can solve, yes. But he's saying, let's just try 2. We already had 2. 2 standard deviations for Chebyshev's theorem gives me 0.75. So, you want to try something besides 2? Maybe 3? 2.5, 3? What do you want to try first, 3? Okay, so 1 minus 1 over 3 squared would be 1 minus 1 ninth, which is 8 ninths. And what is 8 ninths? It's 0.8888888888. You know a kid taught me that? Which rounds to 0.89. Did y'all hear me? A student taught me this. He was on math team at a school. And he said, you don't have to type that in a calculator. I'm like, what? You have that memorized? He said, yeah, because if it's ninths, if you're dividing by 9, it's going to be point repeating whatever the numerator is. So 1 ninth is 0.11111. 2 ninths is 0.22222. What's 3 ninths? 0.333, which is because it's a third, right? You see what I'm saying? Isn't that neat? Did y'all know that? I didn't know that. You memorized what?
The fine, which is whatever, like, the tattoo was, multiplied by 2 on the top, and then it's 0.4.
Right, because you convert the bottom to a 10, so it's 4 tenths if it's 2 fifths. Yeah, I like it. So, y'all, what did I just discover? At least 89% will be between what values? Well, how do I figure that out? How do I figure that out? Do you know how many standard deviations you're using now? How many? 3. So I want to know within 3 standard deviations what values are between it. So what do I literally have to do? I take the mean plus or minus 3 standard deviations. So what can I do? 3 times what? 4.6. Now, you can do it what you were saying, which was subtract. Do you hear them? You can do 20.8 minus 4.6 minus 4.6 minus 4.6 3 times. Or you can just do this, which may be easier. You know what I mean? So what is 3 times 4.6? 13.8. Do y'all agree with him? So if I split that and do 20.8 minus 13.8 and then 20.8 plus 13.8. Okay. So what do I get? 7. And say it again. 34.6. So according to Chebyshev's theorem, at least 89% of high school graduates' ACT scores in science and reasoning will be between 7 and 34.6. Isn't that cool? And you can use Chebyshev's because it works for any distribution. Now the next question says, if we know that ACT scores are normally distributed, then what percent of ACT science reasoning scores are between 11.6 and 30? We know it's a normal distribution, so automatically in my brain, I'm thinking what? Empirical rule, which is? Within 1 standard, I cannot get it right. There we go. Within 1 standard deviation is at least how much? 68%. Within 2? 95. And within 3? 99. So let's see. If it's normally distributed, what percent are between 11.6 and 30? Will I get those numbers if I just add and subtract? I don't know. Let's look. If the middle is 20.8, I'm trying to get to 11.6 and 30. So I'm going to subtract 4.6. Well, if I subtract 4.6 one time, what do I get? 16.2. If I subtract 4.6 again, what do I get? 11. Yay! Why am I happy? Because it's less work. If I don't get 11.6, I'm first going to have to convert it to a z-score, then I'm going to have to use a chart. You see what I'm saying? So we want it to be on here so we don't have to do that work. Okay, how about 20.8 plus 4.6? Isn't it 4.6? Yeah. 25.4. Add 4.6 one more time. 30. Is life good? Very good, because look, that's how many standard deviations above and below. 2 below, 2 above, which means I use right here. If we know that, what percent? Yep, 95%. Everybody good? Okay, I added this example. I pulled this actually from some of my former students' project one time. They wanted to see how much each state spent per pupil on the students, like how much money they invested in the students. They wanted to see if that makes a difference in how well students perform on things. You know what I mean? So this is the raw data. I do want you to have some class time, so let me just back up. Does everybody understand this? Like how we figured out what percentage of the data values fell within 1 and then within 2? Okay, so I'm going to save this example until next class because I think you're good because of this one, okay?